Anyway, seeing no further questions, we are going to move on. So this is on page 20 of your unit handout. It is the final lesson, and we are going to be solving a variety of equations here. Some will be logarithmic, some will be, I hate to break it to you, combinations of logarithmic with trigonometric. I mean, there are different scenarios that we can encounter. Some will be logarithmic and quadratic. What I'm trying to do is hit the different types of questions that you would see on an exam. So the strategy in solving A and also B is very similar to the strategy I just talked about with exponential. A couple of minutes ago, I said that our goal in solving a particular exponential equation was to get 3 raised to an exponent equals 3 raised to an apparently different looking exponent. But then since these are equal, if the bases are the same, then the exponents must be the same, right? It's not that I'm dividing both sides by 3 or anything. I'm just saying, logically speaking, those exponents have to be equal. Well, that's exactly what's going on in A. A doesn't even rise to the level of making it on an exam. It's just an introductory idea that if the base 6 logarithm of 2x minus 1 is equal to the base 6 logarithm of 11, then since these are equal, since the operations are the same, right? I don't want to say log base 6 is a thing that's equal to log base 6. It's an operation. Since both of the operations are equal, then the arguments have to be equal. So 2x minus 1 has to equal 11. And that means I get 2x equals 12, and then I get x equals 6. Are you with me on that? Okay. Except there is always the potential for values that don't work, because arguments cannot be 0 or negative. So you need to get in the habit, whether you're told to or not, of looking at your restrictions in the equation. And basically, whenever you have a logarithm of an argument, the argument must be greater than 0. I'm going to quickly go over why that is, again, just quickly, using an illustration that has numbers in it. If I had log base 2 of 0, I'm asking you to what do you raise 2 to get 0? It's impossible. A positive base raised to any number that's a real number will never give you 0. If I raise that 2 to the 0, I don't get 0, I get 1. If I raise this 2 to a positive number, it's still positive and it just gets bigger. And if I raise that 2 to a negative number, it's still positive, just smaller. Right? 2 to the negative 8 means 1 over 2 to the 8, but this is still positive. It never reaches 0. Right? There's an asymptote on an exponential function of the form 2 to the x. There's an asymptote at y equals 0. And similarly, if I said, this is equal to negative 6, you cannot raise a positive number to an exponent and expect to get a negative result. So the argument must always be positive. What is our restriction in this first example then? If you look at the top of the screen, I'll just bring this up a little bit. If you look at the top of the screen, we have an argument of 2x minus 1, which must be greater than 0. So if I solve that, I get x has to be greater than a half. And I know that at this level, this shouldn't be a problem, but I think a visual is often helpful. There we go. A visual is often helpful. What does this x is greater than a half mean? It means that any value of x we get must be greater than a half. This is the statement of the domain, if you like. This is the domain of the base 6 logarithm of 2x minus 1. Right? This line is x. And what did we get for x? We got x equals 6. It's poking out at the top of the screen there. So is 6 an allowable value? Yes, because it is in fact greater than a half. Any questions with A? All right, B is just one step away from being like A. And here's the step. I don't need brackets around either of those, but I prefer the brackets, particularly around the 4x. What I did there is I used the law of logarithms. It says the logarithm of m plus the logarithm of n is the logarithm of mn. Right? The sum of logarithms is the logarithm of a product. Yes?
Our question says n equals log base 7 of 12, not log base 7 of 2.
Yours says 12? Thank you for that. Oh, okay. For whatever reason last semester, last time I taught this, I finished the question and I said, what if it would have been a 2? Does it say, yours says 12? Okay. So, and then maybe I edited it to be 42. I don't know, but it says 12. That's what you're saying. Okay. Are we okay with that so far? So all I've done is I've used the sum of logarithms equals the logarithm of a product rule. And now I can say, since the operations are the same, it's a base 7 logarithm, I can solve for x and get x equals 3. What is the restriction here on x? Well, any argument that has x needs to be bigger than 0. And the only argument that has x is in fact x itself. So x must be greater than 0. Is 3 greater than 0? Yes. And I should have done this here. Right? I should have indicated that 6 was a solution because it was in the domain of allowable values. And 3 is a solution because it's in the domain of allowable values. Any questions with B? And thank you for that, Ashira. Let's take a look at C. This is different. So I want to try to give you a strategy here that's going to work no matter what. If you have something that can be turned into an equation that has a logarithm that's using a particular base equals a similar base logarithm of an apparently different looking thing, then you can drop the logarithms and say that whatever this argument is and whatever this argument is, whatever they are, they have to be equal to each other to make the equation equal. So this is kind of like a common base thing, but it's common logarithms. And the instant I said that, I regretted it. It's not a common logarithm like a base 10 logarithm. That's not what I meant. I meant the same logarithm on both sides. Okay? But this equation in C does not have a logarithm on the other side. Well, that's okay, because we can write this as 2 raised to the 4 equals x plus 3 squared. And what I'm telling you is, instead of this, if you have this, where you have a logarithm on one side but not on the other, just change it to exponential form, and then you're solving an exponential equation. Right? This becomes p to the dog equals cat. So there's two kind of strategies that are unfolding here. Logarithm equals logarithm, drop the logs and set the arguments equal. Logarithm equals non-logarithm, write it in exponential form. So what do I get here? I get 2 to the 4, which is 16, equals x squared plus 3x plus 3x plus 9. It's never too late to fix misconceptions. I hope nobody has the misconception that x plus 3 squared is x squared plus 9. Right? You write that if you want to give your math teacher an aneurysm. Okay? It's x plus 3 times x plus 3. So we have a quadratic equation where x squared plus 6x minus 7 is equal to 0. How is my arithmetic there? Just sometimes I doubt myself. 9 minus 16 is negative 7. This factors. So we get 0 equals x, I guess, plus 7, x minus 1, which means x plus 7 is 0, x minus 1 is 0. Showing an awful lot of work here. Are you in agreement with the algebra there that I've done? I hope. Okay. Are there any extraneous roots? This is tricky because the way this is written is a little deceiving. This goes back to me telling you, I think, particularly when the argument is a power, that you ought to have a set of brackets around that whole argument. You don't need to. It's not a rule. If you don't write it on an exam, nobody's going to look at it and go, that's wrong. It's still right. But the bottom line here is our argument is x plus 3 quantity squared. It doesn't matter what x is. When you square it, it's going to become positive. Now, I did just misspeak. There is one value of x that you are not allowed to use, and it's negative 3. Because at negative 3 plus 3 is 0, 0 squared is 0, can't take the log of 0. But can I put, what was one of them? Was it negative 7? Can I put negative 7 in for x and evaluate this logarithm? Yes, because negative 7 plus 3 is negative 4, and when you square that, you're going to get a positive. So that squared changes things. Bottom line is both of these answers are correct. Any questions with C? All right, D. Well, we don't have a situation where we have a log equals a log, and we don't have a situation where we have a log equals a non-log yet. I can subtract log of x plus 1 from both sides. So I have log of 8x plus 4 minus log of x plus 1 equals to 1. We're moving all the logs to one side so I can combine them into a single log, then I can write it in exponential form. So I end up with the logarithm of 8x plus 4 over x plus 1 equals 1. And now, everybody, it is the case that we have on the right here. A logarithm equals a non-logarithm. So I can write this in exponential form, but I need to remember that a common log, which is when you're not told what the base is, it's understood that that common log is 10. So now I can write 10 to the 1 equals that argument. Well, 10 to the 1 is 10. I'm not going to rewrite it just so I can write 10. And now I have a rational equation. I would like to get rid of the denominators. You probably know me by now with regards to cross multiplication. I just don't like the idea of it. But I do like a more general idea, that is, you don't want denominators. You don't want denominators. So we can multiply both sides of this equation by x plus 1. Sometimes you can't avoid it in math, but with an equation you certainly can. The x plus 1's cancel, and you're left with 8x plus 4 equals 10 times x plus 1. I know we could have just cross multiplied. I'm aware of that. I just don't like it. Because people, you can get lazy and think you can cross multiply all the time, and it doesn't always work. Now I can solve this pretty simple. 8x plus 4 equals 10x plus 10. I have more x's on the right side, so I'm going to subtract 8x from both sides. And I'm going to get 4 minus 10, which is negative 6. I want to double check. I didn't stop and double check any of these. X plus 1, I'm subtracting. It's over that. 10 to the 1. We're okay. So we get x equals negative 3. Good with the algebra. Okay. What about the restrictions? So you may not be asked to do the restrictions on a written response. It's your responsibility to look at them. All right, let's take a look at another one. Well, it's the same kind of thing. I'm going to get the logarithms together. Log base 2 of x minus 6 plus log base 2 of x minus 4 equals 3. But this time I'm going to have log base 2 of x minus 6 times x minus 4 equals 3. And by the way, the first argument, argument 1, tells us that x must be greater than 6. The second argument, question?
I just have a question about the last one.
Yep.
So you said
So are we in agreement on those two restrictions? Okay. So Brooke, if I were to draw a number line here, and I put negative 1/2 here, where would I put negative 1? Excellent. Thank you, Brooke. We need a value of x that is both greater than negative 1 and greater than negative 1/2. So does it make sense to you that we need to have a number greater than 1/2, negative 1/2, to in fact be greater than both? Okay. And trust me, it's really easy to mix things up when you solve these problems. So our overriding restriction is x is greater than negative 1/2, but negative 3 is not greater than negative 1/2, which means negative 3 has magically been crossed off the list already. Okay. In all seriousness, thank you for that, correcting that. That's important. Okay. Are we okay now with that question? Okay. Let's get back to E. So what we're doing here is we're combining the logarithms, and the restrictions for the first argument lead us to x is greater than 6, and for the second argument lead us to x is greater than 4. We're okay with that? Let's see if I can manage to put the numbers 4 and 6 on a number line this time in the proper order. I think I got this one. What we're saying is x must be greater than 4 and x must be greater than 6. So a number like 5 is not an allowable value of x because although it's greater than 4, it's not greater than 6. So again, it's the overlap. Our restriction here, our overriding restriction is x is greater than 6. Let's keep that in mind as we solve this. This is 2 to the 3 equals x minus 6 times x minus 4. So I'm going to FOIL this out. 2 to the 3 is 8, and I get x squared minus 10x plus 24. Pretty sure that's okay. It's quadratic, so I'm going to zero the equation to get x squared minus 10x plus, help, 16, thank you, equals 0. I guess 2 and 8, well, negative 2 and negative 8 would do the trick for factoring. Which means x equals 2. Not really, because 2 is not permissible. We'll come back to that. And x equals 8. But again, here's our overriding restriction. This is our domain of allowable values of x for the whole equation. And 2 is not a number greater than 6, but 8 is a number greater than 6. So this one is out, and this one is in. Good? Okay. All right, so just maybe don't write anything down just for a second here. F log base 3 of x squared minus 8x to the 5. What this actually means is that, right? So I guess you have an option. You could do this. You could say 3 to the 10 equals x squared minus 8x to the 5. But then you have to do that. Getting a degree 10 polynomial function. Imagine you had the wherewithal to multiply that all out anyway. You're going to get a degree 10 polynomial function, and the constant term when we move this 3 to the 10 over is going to be negative of whatever 3 to the 10 is, and then you're going to use the factor theorem and synthetic division to try to solve this. But it's degree 10. So, you could be doing synthetic division 7 or 8 times. So that's not what you're going to do. What you're going to do instead is the following. We're going to bring that 5 out in front. So that we can divide both sides by 5 and deal with a smaller exponent. I divide both sides by 5 and I get 2 here. So I have log base 3 of x squared minus 8x equals 2. Just be very careful, and I'm just telling you this from experience. The number of times students confuse these two things is too many. Right? Just stop and think. I mean, you see a 3 and a 2, sometimes you just go, oh, 9. Well, in this case, it is 9, but if it were 2 to the 3, it would be 8. So be very careful. This is going to be 3 raised to the 2 equals x squared minus 8x. So x squared minus 8x minus 9 equals 0. I believe it factors into x minus 9, x plus 1. Pretty sure that's right. Which means x minus 9 equals 0 or x equals 9. X plus 1 equals 0 or x equals negative 1. And now we have really a difficult problem. Because the question about the restriction boils down to where is that greater than 0? And because it was raised to a 5, which is an odd number, we don't need to include the 5, because if this is negative or 0, raised to the 5 will be negative or 0. So how do we decide where this is positive and where this is 0 and where this is negative? The answer is we factor it and we visualize this x times x minus 8 as a parabola. There is no y here. There is no y. But what if it was equal to y? Well, it would have an x-intercept of 0, and it would have an x-intercept of 8, and it would open up. Which means x squared minus 8x looks like this. So where is it greater than 0? It's greater than 0 whenever x is greater than 8, because then the parabola is above the x-axis where it's positive, and wherever x is less than 0. In other words, if it is a number, if it's 0, it makes the argument 0, which is out. If it's 8, it makes the argument 0, which is out. If it's a number between 0 and 8, the argument becomes negative, so that's out. The number has to be either less than 0 or greater than 8. If that's troublesome, and solving quadratic inequalities is a tough thing. You learn it in Math 20, but it just flies past a lot of people. Then simply go back up to the original equation and put 9 in and ask yourself if you get a positive or a negative. And then put negative 1 in and ask yourself if you get a positive or a negative. Any questions with that one? All right. I would like everybody to look at this very carefully and see if you can figure out what the important difference is between the first term in this equation and the second term in this equation. I mean, the important difference, I guess, in answering my own question is this, but why does that matter? How are these two different in terms of what we are allowed to do from here on in? Anna?
The entire logarithm is squared on the left side, whereas it's just the x that's squared on the right side.
So the entire logarithm in the first term is squared, but only the x as part of the argument is squared in the second. What are we allowed to do in the second one then?
Bring the two out in front.
Right. Because in the first term that exponent is not on the argument but on the entire log, we can't do anything with it. But in the second term, we can apply. Remember me talking about, I wish we could do this? Okay, well, I've asked around and it's not going to happen. Okay, so we got to go with that. I'm going to bring that 2 down. And now I have a quadratic equation. If you had a squared minus 2a equals 0, you'd factor an a out and say a equals 0 and a equals 2. Just, this is your eyeball. Just eyeball that series of lines and think about what I'm telling you. A squared minus 2a is solvable. It's a very basic Math 20 kind of quadratic equation to solve by factoring. Well, this is no different, but instead of factoring an a out, I'm going to factor a log of x out. And that means log of x equals 0, and log of x minus 2 equals 0. I hope it's obvious that second factor is not log of x minus 2. It's log of x minus 2. Right, the 2 is not part of the argument. So this becomes log of x equals 2. Where do we go from here? Alex?
Convert it to exponential.
What am I missing here? Like what's not visual? How are you going to convert it to exponential?
The base 10.
Right, it's a common logarithm of base 10. So when we convert this to exponential, we have our answer. Yeah,
Ours has a base 2.
yours has a base 2 throughout the whole thing?
Yeah.
Oh. Ask and ye shall receive. So this is base 2 everywhere. So when we convert this to exponential, we're going to get 2 to the 0 equals x, and 2 to the 2 equals x. So we get x equals 1, 2 to the 0 is 1, and x equals 4. And if you look at the restrictions on the variables, there were log of x's, which means x must be greater than 0. 1 and 4 are both greater than 0, so they are both solutions. Let's try one more, I believe, that's going to be quadratic as well. Same thing. This is log of x quantity squared minus 5 log of x minus 24 equals 0. Can you confirm that it is a common log in this question, not a base 2 or 3? Or okay. So we're going to factor this. This is not a difficult question at this point in time. Once you've seen it once or twice, it will stick. This will factor into log of x, log of x. We need two numbers that multiply to give negative 24 and add to give negative 5. So we get that. Just get this out of the way. The only argument is x. I know that there's an x to the 5, but 5 is an odd exponent. So as long as x is greater than 0, x to the 5 will be greater than 0. There's no other way to get positives. Log of x equals 8, and log of x equals negative 3. These are base 10. So now I can go 10 to the 8 and 10 to the negative 3. Both of these numbers, 10 to the 8 and 10 to the negative 3, are positive. So they are in that restriction that I have at the top right of the screen. Any questions with h? All right, and I, because why not? Okay? Logarithmic, trigonometric. I guess I could pile on a quadratic if I wanted to, but we'll save that for the exam. Maybe. How do we solve this? Well, let's rearrange for the thing that has x in it. So I'm simply going to move the 2 to the other side. And then divide both sides by 4. Then I have a fighting chance. And this is not a difficult, well, I was going to say this is not a difficult question. This is Math 30. Everything we do can be difficult, right? But this is not like outside of the boundaries of what you would be expected to do on an exam. This is negative 1/2. So I get log base 2 of cosine of x is equal to negative 1/2. Brackets around the cos x or not, it's kind of your choice. So now let's write it into exponential form in the hopes that it becomes easier to think about. And I'm going to have 2 raised to the negative half equals cosine of x. What does that mean? It means 1 over 2 to the positive half is cosine of x, which is 1 over root 2, which you should recognize as a point on the unit circle. You know, we're back in trig right now. Where is cosine of x 1 over root 2? It's 1 over root 2 at the 45-degree reference point here and here, because these coordinates are 1 over root 2. So what are we going to say? We're going to say pi over 4 and 7 pi over 4. We weren't given a domain here. Like with trig functions, sometimes you see 0 to 2 pi. We weren't told that, which means our solutions need to be extended into a general statement. And now, just to finish this off, what about the restrictions? Well, when you take a look at the original equation, the argument on the logarithm was cosine of x. Correct? And I'll highlight it for us. The argument is cosine of x. So the restriction here is that cosine of x must be greater than 0. But in all of our solutions it is. Be careful here, because I almost just got in a trap here in my head. I said, whoa, wait a minute, this includes negative angles, doesn't it? It does include negative angles. But they all land in a position where the cosine is positive. And that's it. Are there situations you can encounter that we haven't seen in these examples? Probably. Those people at Alberta Ed can be pretty devious and crafty about coming up with questions. And sometimes I'll see a question that I've never thought of, and then next time I try to include it. But the bottom line is you have 2 different strategies here, and then we're also talking about quadratics. But if you can get it so a logarithm is equal to the same base logarithm, then the arguments are equal. If you can't, but it's a logarithm equals a non-logarithm, put it into exponential form. Don't do 21. If you want to give 21 a crack, feel free. But the thing that makes 21 difficult is they have different bases in the logarithms. And you're not expected to be able to do that.